Hello, everybody. It's time to talk about perhaps my favorite topic in all of astronomy, comets. I'm going to do my best to not get overly excited in this video. I'm not going to make you any promises, though. Let's get started with just an introduction to comets. Of course, I could teach an entire class on comets. It happens to be my primary area of research. It is what I wrote my dissertation on. It is what I have been academically obsessed with for going on 15 plus years. Okay, so comets. Let's cover what they are and how they do their orbits, how they become active, and really, let's take a moment to appreciate just how amazing comets are when they become naked eye visible objects. It's a very rare event. We only have a few great comets, maybe on average about once per decade, two per decade if we're lucky. And a great comet are the ones where you walk outside and you can just see with the naked eye, and they create some pretty amazing sights out in the night sky. Uh, the one that personally hooked me in 1997, my dad took me up to Foothills Parkway. If you're local, you might know where Foothills Parkway is. It's not too far. It's a good place close to campus, about a 45-minute drive where you can actually go see some dark skies. Went up there to go look at Comet Hale-Bopp. We didn't have to go to Foothills Parkway to see it. We could see it pretty much anywhere. And in fact, Hale-Bopp was so bright that it could be seen in broad daylight. But regardless, we went up and I remember seeing Hale-Bopp. And there's, I guess, something in my brain, like a seed was planted. And I think that event is linked to the fact that whenever I went to graduate school, I ended up writing my dissertation on comets and on Hale-Bopp itself. So here is a picture of Comet Hale-Bopp over Mono Lake out in California, over by Yosemite. Absolutely stunning. Of course, this is taken with a camera and it's a long exposure. It did not quite look like this naked eye, but you could see both tails pretty easily. A truly stunning night sky object. This is Comet McNaught, the great comet of 2007, viewable from the southern hemisphere, not really from the northern hemisphere. And it was quite known for having this very extensive tail that spread out across the sky. Again, you have to use long exposure photography to get an image like this. Most of the time, comets are not great comets, they're just regular old comets. And I want to include a picture of that. This is Comet Lovejoy, or one of the many comets called Lovejoy. They're named after the people or the facility that discovers them. And this is right here. Typically, when you look at through binoculars or a telescope, you'll get a view of a comet that looks like this. You won't have detail like this in the tail, so you can see the dust tail, and it has some sinuosity. You can see a lot of details in there. And then you can see a brightly green glowing coma in this case, and it's glowing green due to emission from oxygen atoms. And then there's the most famous comet of them all, Comet 1P Halley, Halley's Comet, that comes around every 76 years or so. And this is its apparition in 1986. We won't have another one until the 2060s, so hang on tight, and hopefully we'll all get to see Halley's Comet if we're all lucky in the future. So truly stunning night sky objects. There's a lot going on with them. All of these are comets whenever they're active, and we're going to have to cover what that means. But let's just go ahead and start with a simple idea of what are comets and how you can think about them. What kind of materials do they contain, and what is a good model, something to put in your head and picture a comet as? So comets are small objects. They're rocky, icy objects. They have lots of dust too. But the dust is rocky or it has organic molecules. It's a subcomponent. So you have rock, ice, and dust that make up comets. And they're fairly small objects. They're hundreds of meters in diameters to perhaps a few tens of kilometers. So they're small objects in the solar system, and they have highly eccentric orbits, which means that sometimes they're very close to the sun. Their perihelion points very close to the sun, and their aphelion points very far away from the sun. So they don't have very circular orbits. They have extremely elliptical orbits, high eccentricity orbits. And you can think of a comet. A common thing that's thrown around is what's called the dirty snowball model of comets. Why a dirty snowball? Because that is a pretty good approximation of what a comet is made out of. So we have the dirty snowball of comets because the composition of comets are very similar to if you went outside and made a dirty snowball. If you went outside and you had some snow that fell, so you got some snow, water ice, crunched it into a snowball, but you made sure to mix in a little bit of dirt, some rocks as well. Maybe you mixed in a little bit of organic material, so there was soil as organic material in it, and you squeeze that all together. You'd have a pretty good approximation of what a comet is made out of. Because a comet is made out of rock, dust, water ice, primarily. And then it has significant quantities of colder temperature ices as well, like carbon dioxide ice, carbon monoxide ice, nitrogen ice, methane ice. All of these ices we don't really run into here on Earth because Earth is pretty warm. And we can't get temperatures down cold enough, and never naturally gets cold enough on Earth to form carbon dioxide ice. Although you've probably interacted with it, if you've ever had food and handled food that was packed in dry ice, that's carbon dioxide ice. So dry ice is CO2 ice. So comets are rock, dust, water ice, and then a significant amount of colder temperature ices, exotic ices, low temperature ices, and the exciting bit, organic molecules. Not life, organic molecules, carbon bearing molecules. So I already talked about some of the low temperature ices that are in comets. What are some of the organic molecules? And this is where things get super duper exciting, at least for me, because we're talking about water ice and organics. And we're wondering where Earth got water ice and organics. Hey, here's a natural delivery system. But we have things like simple hydrocarbons, things that you don't get too excited about, like methane and ethane. You have some things like graphite as well, just carbon chains. Then you have more complex organics. So you might have some nitriles running around there, alcohols, other complex organics as well. I am not an organic chemist, so I can't give you a really good list here. And then you have some really complex organics, something absolutely exciting, that on the surface of this comet that we're looking at on this slide, and in the comey of other comets, parts of the other comets, we have had positive detections of the simplest of the amino acids, the precursors to things like proteins. And that is glycine has been detected on this comet right here, the comet we probably know the most about, because in 2014, the European Space Agency, the ESA, sent a spacecraft called Rosetta, which orbited this comet as it came close to the sun and approached perihelion, and then as it left perihelion as well. So it saw the full activity cycle of this comet. Let's see if we can say the name. So this comet is Comet 67P Churyumov-Gerasimenko. I almost want to give people bonus points if they can make a video of that and send it to me, pronouncing it correctly. So 67P Churyumov-Gerasimenko. We usually just say 67P CG for short. But think about that. We have complex organic molecules, including the simplest of the amino acids. There are some famous experiments called the Urey experiments. I encourage you to go look that up if you're curious, where people were trying to take basically the primitive kind of stuff we find in space and then put it in conditions that similar to the early Earth, so like warm water with some energy sources, and see what kind of organic chemistry you get coming out of it. They've repeated those experiments with cometary material, the kind of organics that we find here on 67P CG and other comets. Put them in a warm bath, maybe pass some electricity through there to give some energy or provide some other energy sources, like maybe simulate some hydrothermal vents and see what kind of organic chemistry happens. And in those experiments, you can reproduce every single amino acid that we currently know of from the organics we find on comets. Super, super cool stuff here. Also super cool stuff in the presence that it has these super cold ices, things like this nitrogen ice, which disappear. They stop being an ice because ices need to be cold, right? And if you get ices too warm, they're no longer ice. And things like nitrogen ice and carbon monoxide ice, the presence that they're actually in comets means that these comets have never gotten warmer than their melting point, their sublimation point, about 50 Kelvin or so for the cold ices we see there. That's getting down towards absolute zero, 50 Kelvin, super cold. The air in this room right now is about 290 Kelvin. And these comets have never been warmer than 50 Kelvin. Otherwise, if they ever got warmer, those ices would have disappeared. So the very fact that we observe those ices in these comets means that they essentially have been super cold ever since they first formed. And we can take a look at these comets, and essentially it's just whatever particles that built our solar system came together to form the comets, locking in these ices and these dust particles, these original solids of the solar system. And they have basically been in deep freeze for the past 4.5 billion years. So comets are deep freezers of space, preserving the original ingredients that our solar system was built out of. It's because of comets are these deep freezers that we refer to comets as the most primitive objects in the solar system. You want to sample what all the planets were built out of? You want to sample what the original solids of the solar system were, what the original building blocks and ingredients that we make our solar system out of? Just take a look at comets, which is what I strive to do, or increase our capacity and our ability to determine some of those building block ingredients by examining comets, doing a spectral analysis in the infrared to identify silicates in comets. That was the topic of my dissertation. All right, so moving on. I said I wasn't going to get too excited. Look, here we are. I'm super excited. So comets are, for it to be a comet, it needs to be active. There are plenty of things out in the solar system that have the potential to be a comet, but they never get close enough to the sun to become active, and therefore they are technically not a comet. So for something to be an object to be a comet, it needs to have a high eccentricity such that it'll come close to the sun near its perihelion, close enough where some of those ices that are in comets can go from being an ice to turning into a gas. And whenever it turns into a gas, it'll pick up the dust particles that are on the surface and little bits of those rock, and the gases themselves will then form a temporary atmosphere around the comet. And at that point, we say the comet has become active. And unless there is this activity, an object cannot be considered a comet, which means that all comets have very high eccentricities. We'll get to the difference between short period comets and long period comets in a moment, but there are two different types. Short period, they have short periods, less than 100 years. And then long period comets, they have orbital periods greater than 100 years. Man, we're good at this. So short period comets typically have eccentricities of about 0.2 up to about 0.7. Long period comets have very, very high eccentricities, getting close to 1, 0.95. Comet Hale-Bopp, which came from the Oort cloud, had a very, 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 very high eccentricity, something like 0.99997. I think I got that right. Don't quote me on it. So this means that comets have orbits with high eccentricities, which means sometimes they're very close to the sun, near their perihelion point. So their perihelion point is very close to the sun. Their aphelion point is way far away from the sun. And this controls their activity cycle. So for a comet to be active, as I was just saying, that means that the ices that are in the comet, especially the ones right near the surface, on the surface or just below the surface, are going to get warm enough to no longer be an ice. And they don't go through a liquid phase. There's just, you can't really do that in the vacuum of space. So they skip the liquid phase and they go directly from a solid phase to a gaseous phase. Going directly from a solid to a gas, that process is called sublimation. If you've ever left an ice tray in the freezer for too long, you look one day and you have ice cubes, you put it in the freezer, you forget about it for a few months, you pull it out again, and then you have little tiny ice cubes. How do the ice cubes shrink? Well, the water ice went directly from water ice in the ice cube to water vapor in your freezer. And slowly, your ice cubes were sublimating away. You can think about it as vaporizing directly from a solid to a gas. So as the comet gets closer and closer and closer to the sun, it's getting more sunlight, it's going to warm up enough so all of a sudden those gases, those ices sublimate, turn into gases, and the gases leave the surface of the comet, pick up some dust as they go. Oops, wrong button. They pick up some dust as they go, and then that released gas and dust from the surface of the comet forms a temporary atmosphere. The comet itself is too small to have enough gravity to hold on to all the released gas and dust forever. It'll slowly drift away. But it does have enough gravity to sort of hang on to it during its perihelion passage. So that gas and dust that's leaving the surface forms this temporary atmosphere of gas and dust that we call the coma. And that is enshrouding this, encircling the solid part of the comet, the actual celestial object that's creating all this activity, the nucleus of the comet. But we're not done with the activity yet, because now we have gas and dust surrounding the nucleus of the comet. We have this coma. And we have to deal with the sun's light. So sunlight's coming in, which sunlight is made of photons, which can push small things like gas and dust. And then we have this solar wind, this constant stream of particles, protons and electrons flying off the sun, going throughout our solar system. So the solar wind and sunlight will push on the gas and dust that we have in the coma, and it'll push it away from the sun, away from the direction of the sun, forming two different tails. An ion tail, where the gas has been ionized, so it'll make a tail made out of ions. And then we will have a dust tail that's made out of the dust particles that are forming a tail. And of course, it's at this point, whenever you have all of these things, you have a really, really big coma, and then you have the formation of an ion and a dust tail. And then it happens to be close enough to Earth at the same time and close enough to the sun that it can become an astounding night sky object like Hale-Bopp. And I just want to show you some of this activity since the Rosetta spacecraft orbited around 67P CG for a while. We got to see the formation and how activity turns on. And you can see it has numerous jets from the surface of the comet. And that's where the gas is sublimating away rather violently, creating jets of material, spewing gas and dust away from the surface of the comet, which will form a temporary atmosphere that is the coma. And eventually the sunlight will push on those gas and dust particles, forming the two tails of a comet. So let's take a look at what the anatomy of a comet would be. Our small little thing that's only hundreds of meters to maybe a few kilometers in size, the solid bit that's orbiting the sun, that's what we call the nucleus of the comet. That's the solid, dirty snowball. When the comet gets close to the sun and becomes active, those ices turn into gases, form a temporary atmosphere of gas, pick up some dust, and put some dust in this temporary atmosphere, which we picture as spherical around the nucleus. And that's our coma. Then sunlight comes streaming through and solar wind comes streaming through. The solar wind is made out of charged particles, which will push on the ions in forming the ion tail, push the ion tail directly away from the sun. The dust particles are pushed by light, photon pressure, pushed away from the comet or the nucleus in the coma, and they will form a dust tail that's slightly offset from the ion tail. It's a gentler push, and we're dealing with solid things that are trying to remain in orbit. So this gives us our parts of the comet: the solid, dirty snowball part, the nucleus, the temporary atmosphere that forms as the comet becomes active, the coma, and then we'll get the formation with interactions of sunlight and the solar wind forming the ion tail and the dust tail. So this is just a cartoon drawing of a comet that I made. How does this actually compare to reality? Here's Comet Hale-Bopp near the peak of its activity. So you can't see the nucleus right now. It's buried behind, you're seeing reflected light, reflected sunlight, but the central region right here would be where the coma is. Here we have the dust tail. It's bright because there's sunlight reflecting off of the dust. It also makes it white in color. And here we see the ion tail, which has a nice bluish color due to certain electron transitions as those electrons come back onto the atoms and then cascade down towards the ground state, emitting light. So this one is directed directly away from the sun, and this one's slightly curved. The dust tail is slightly curved. The ion tail is directly away from the sun. Which gives us a rather interesting thing, because now we can consider the direction of the tails of a comet. Everybody thinks a tail is what follows behind you, right? Except that's not the case for a comet. The direction of a tail is pointed away from the sun, because that is, it's actually sunlight and the solar wind, which is streaming away from the sun, that create the tails. It's material being pushed by solar wind and sunlight. So that means as the comet is coming in on its highly eccentric orbit, that's why it looks like this, as it's coming in towards perihelion, the comet's traveling this way. Here comes sunlight, and it'll create the ion tail, which is directly away from the sun, and the dust tail made out of solid bits that are trying to maintain their orbit. So you have a slight curve to the dust tail. But in general, they're both pushed away from the sun. And now the tail is actually trailing behind the comet. But then as it swings around here, the ion tail is going in this direction, but the comet's moving in that direction, swings around perihelion. And now let's consider it as it moves away back towards aphelion, away from the sun, going back into the outer part of the solar system. So the comet's moving, the nucleus is moving this way, sunlight's moving pretty much the same direction, pushing the tail that way, pushing the dust tail this way, and the same over here, pushing the ion tail directly away, the dust tail generally away. And here, the comet's tails are leading the comet. They're in front of the comet's direction. If we're saying that in front of, it would mean in the direction that the comet is moving. So the direction of the tails of a comet is always away from the sun. And it's photons and the solar wind that are doing the pushing that creates the tails. All right, now we can get back to our short period comets and our long period comets, because we want to answer the question of where are these comets coming from? These strange, beautiful objects that can grace our skies. So we have two source regions for comets. They are all going to be visitors from the outer solar system. They're all going to be leftovers of outer solar system formation of our solar system, the things that were being built in the regions away from the sun. Well, we have our short period comets, which originate from the Kuiper belt. So Kuiper belt objects made out of rock, they're rocky, icy objects. One of the small ones gets gravitationally perturbed. Maybe it came too close to another one, so it got slung towards the inner solar system. And now it has a highly eccentric orbit, so it can become a comet. So these short period comets have periods of about 200 years or less. And they originate in the Kuiper belt, and they also come from this other region that we call the scattered disk, a little bit too nuanced for what I want to talk about in this class, which gives them semi-major axes of somewhere about 3 to about 1,000 AU. This is getting pretty extreme to be 1,000. I'd cut it off probably more closer to the 100 mark. So if you look at the orbits of the short period comets, they're like everything else pretty much in the solar system, where they all orbit the same direction and they all pretty much lie in the same orbital plane. So they all orbit in the same direction as the planets, and they have relatively low to maybe moderate inclinations, how much they tip above or below that plane of the solar system. And there's estimated billions of potential comets out there in the Kuiper belt, even though very few of them have these eccentric orbits. There's the potential. There are a lot of them out there that could potentially become comets. And then we have our long period comets. These ones have orbital periods of thousands to millions of years. And these are the ones that are originating from the Oort cloud that have semi-major axes and the thousands to tens of thousands of astronomical units. So they're coming from the Oort cloud to visit our solar system. How might an Oort cloud object be put onto an orbit that brings it close to the sun, that brings it coming through the inner parts of the solar system? Lots of things. A star could pass nearby our sun, and the gravitational influence of that star as it moves by our sun could disturb some of these Oort cloud objects and put them on orbits that have high eccentricity that would bring them to the inner solar system. Maybe it's just a cloud of gas that passed nearby. Maybe two of them got too close to one another. So lots of different things. And yes, stars do pass close by. All the stars are moving, and sometimes they get pretty close to our sun. And by sometimes, I'm talking about astronomical timescales on the orders of millions to hundreds of millions of years. But since they're coming from the Oort cloud, which has the spherical distribution, they're not all going to have orbits that are in the same plane as the rest of our solar system. They can come in from any direction. And this is why from any direction, any inclination in any direction, evenly distributed, we call that isotropic, to put a fancy term to it. So sometimes these are called the nearly isotropic comets. There are estimated trillions of objects in the Oort cloud, so there's potentially trillions of these things. And here's a list of some of the examples. Hale-Bopp is on that list. I should have updated this list to add Neowise. Comet Neowise was an Oort cloud comet. So we have our long period comets. And what really is the scary thing, if we want to talk about potential impact hazards for Earth, what got the dinosaurs? Probably an Oort cloud comet. It was a comet, but almost certainly an Oort cloud comet. But why are we scared why should we be, I shouldn't say we should be scared. Why are these the concerning objects if we want to consider things that could cause mass extinction events from outer space through impact? Since these things are coming from the outermost reaches of the solar system, the Oort cloud, so we'll use a comet, Comet Ison, which was supposed to be a great comet, but it died in its perihelion passage around the sun. It took it 2.5 million years to go from its aphelion point in the Oort cloud to its perihelion point, pretty much at the surface of the sun, or very close to it. 2.5 million years. And remember, by Kepler's second law, it's moving really slow when it's far away, and it gets moving really, 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 really fast whenever it gets close to the sun, which means that it's zipped through the entire inner planetary region of the solar system very, very quickly on the scale of weeks. Which means these things are small and they don't become active until they're close to the sun. So we currently have no technology that can visibly see these things to detect them until they're already active. And by the time we can detect them and they're active, they are going to be reaching the inner part of the solar system where the Earth lives in a matter of weeks to months. So we get essentially no forewarning. This is like, oh, wow, we discovered one. Here it is. All right, everybody pay attention to it right now. Okay, so just wanted to share all that wonderful information about comets. I did not live up to my promise. I got overly excited. I made this a long video, but hopefully you got excited about what Dr. Lindsay originally got excited about and wrote his dissertation on. So if you have questions about comets, please add to the week 9 discussion, and I will be happy to share as much information as you possibly could ever want about comets. There are probably only a few dozen people in the world that know more about comets than I do, since I am a cometary specialist. So please ask me questions. All right, thank you for tuning in to this video.